So, this is lecture number 7 of the course on fundamentals of transport processes. In the past 4 lectures, we had looked at some mathematical preliminaries. As I said, our final objective was to derive conservation equations for fluid flow, okay, momentum conservation equations. And since we wanted to treat velocity as a vector rather than looking at the individual components, we were doing some fundamentals of vectors and vector calculus, tensors and tensor calculus. In this lecture, we will try to apply this to fluid flows, okay, in order to get some physical understanding of what these things mean. Okay. So, we will do this without reference to the forces acting on the fluids or the momentum transport, but rather the description of the flow itself. Okay. So, what is called in fluid mechanics as kinematics. The description of fluid flow without reference to the forces that are acting on the fluids. So, the simplest operator that you can look at is the divergence operator acting on the velocity field. Okay. Divergence of, if you know that when we deal with heat and mass transfer, okay, the flux Q is the amount of energy transported per unit area per unit time, per area into time. Okay. So, this flux is a local quantity. It tells you how much energy is transported per unit area per unit time across some surface. Okay. It gives you the direction of the flow of energy. Okay. So, if I take this and integrate it over the surface of some volume, I have a volume V and integrate over the surface. Okay. You know that the total energy coming out of this surface, the energy perpendicular to the surface is q dot n, where n is the unit normal to the surface. N is the unit normal to the surface. Okay. So, therefore, the total energy that comes out of the surface per unit time is integral over the surface of q dot n, okay, the integral over the surface of q dot n. Okay. And you know by the divergence theorem that this can be written as integral over the volume of the divergence of q. Okay. Note that this is an integral. It tells you how much net energy is coming out from inside the surface to outside. Okay. If there is no net energy source within the surface, there is no energy that is coming out from inside to outside. Therefore, the integral over the volume of divergence of q has to be equal to 0. So, divergence of q basically tells you, okay, if you integrate this divergence of q over the volume, it basically tells you whether there is a net source of energy within this volume or not. If there is no net source of energy within this volume, integral of ds q dot n has to be equal to 0. Therefore, the integral of the volume of divergence of q has to be equal to 0. Okay. This is true for any volume. However, if I take the volume going to 0, then I have the divergence of q at that particular point is 0. So, there is no source at that point. Okay. Similarly, if the divergence of q is 0 everywhere, there is no source at any location. Okay. Basically tells you for a given volume whether there is an energy source within that volume or not. Same thing can be done for fluid flow. Okay. The amount of fluid coming out, okay, the amount of fluid at any location is equal to of fluid in volume delta V is equal to rho times delta V. Okay. So, rho is the fluid density, the mass per unit volume of fluid. Okay. For this same surface, okay, rather than looking at the heat that is coming out, if I wanted to know what is the mass of fluid that was coming out of this volume, okay, the mass flux that is coming out of this volume is rho times u, okay, which is mass per unit area into time. That is the flux of mass that is coming out of this volume. It is the amount of mass coming out per unit area per unit time. So, if I want to find out the total mass that is coming out of this volume from inside to outside, okay, the total mass that is coming out of the volume from inside to outside, that has to be equal to integral ds of rho u dotted with the unit normal n. Okay. And from the divergence theorem, I know that this is equal to integral dv of divergence of rho u. Note that the divergence theorem, if I have some quantity dotted with n, okay, I have integral of the surface of something dotted with n is equal to the volume integral of the divergence of that whole thing. Okay, you cannot just take divergence of part of that. Okay, so, it has to be the divergence of the whole thing. So, this gives me the total mass of fluid that is coming out. Obviously, if there is fluid mass coming out from inside to outside, there has to be some mass source inside this volume. Okay. If there is no mass source within this volume, okay, then this thing has to be equal to 0, which means that this also has to be equal to 0. So, if there is no mass source within the volume, then this has to be equal to 0. Okay. Further, if the fluid is also what is called incompressible, okay, if there is no mass source anywhere, and if the fluid is also incompressible, okay, that is constant density. If the fluid is also incompressible, which means that the density is a constant, then I require that divergence of u is equal to 0 or del dot u is equal to 0. Okay. For an incompressible fluid, okay, if there are no sources of mass anywhere within the volume, that means that the divergence of u has to be equal to 0. Okay. So, let us look at what the divergence means. Okay. If I have some spherical surface, okay, if I have some spherical surface around the origin, okay, at some location I have some this distance r and I have a velocity field u vector. Okay. If this velocity field is along the direction of the radius vector, okay, that means that u vector is equal to u r e r. Okay. It is easier for us to do it in just 2 dimensions to make the point. So, rather than doing a 3-dimensional system, I will just restrict attention to a 2-dimensional system with just 2 coordinates, okay, because it is easier to make the point in 2 dimensions. Okay, this is x 1 and x 2, and I have some surface, some circular surface, okay, of constant distance from the origin. Okay. And the velocity u vector is equal to u r times E r. Okay. Now, this E r vector can be resolved in terms of the 2 components. Okay. E r can be resolved in terms of its 2 components. So, if this is the angle made with respect to the x 1 axis of this radius vector, okay, then you know that E r is equal to E 1 cos phi plus E 2 sin phi. Okay. E phi is perpendicular to this. Okay. In this polar coordinate system, E phi is perpendicular to this, which means that E phi is equal to minus E 1 sin phi plus E 2 cos phi. Okay. E r and E phi are mutually perpendicular vectors. Okay. So, now I can write u in terms of E r and E phi. Okay. Also note that this radius vector is r. Okay. This radius vector is r. That means that r is equal to square root of x 1 square plus x 2 square, and x 1 is equal to r cos phi, x 2 is equal to r sin phi. Okay. Okay. So, these are the components of the x1 and x2 in terms of r and phi. Okay. So, u vector is equal to u r times E r. Okay. So, u vector is equal to u r times E r, which is equal to u r into E r is E 1 cos phi plus E 2 sin phi, okay, which means that u 1 is equal to u r cos phi and u 2 is equal to u r sin phi. Okay. So, writing cos phi and sin phi in terms of x 1 and x 2, okay, writing cos phi and sin phi in terms of x 1 and x 2, you get that u 1 is equal to u r times x 1 by r plus and u 2 is equal to u r times x 2 by r. Okay. That is, the velocity is along the outward radius vector. Okay. If the velocity increases proportional to r itself, okay, if the velocity increases proportional to r itself, that is, if this is equal to some constant times r times E r, this is equal to some constant times r times E r, that is, as you go outward, the velocity is increasing with distance outward. It is increasing proportional to r itself. Okay. So, then for this case you will get u 1 is equal to c x 1, u 2 is equal to c x 2. And what is the divergence of u? It is partial u 1 by partial x 1 plus partial u 2 by partial x 2. Okay. So, that means that divergence of u is equal to partial u 1 by partial x 1 plus partial u 2 by partial x 2 is equal to 2 times c. Okay. So, the divergence is non-zero only if the velocity is increasing as you go outwards. Okay. As you go outwards, the velocity keeps increasing. Okay. So, that means that the divergence of u is non-zero. Okay. That means the velocity field is diverging from this point, okay, as you go outwards. Okay. If divergence of u is 0, there is no net flow out of this surface. Okay. So, that is the physical meaning of divergence. There can be a net flow out of a surface only if there is some source within that surface which is generating that net flow. Okay. So, the divergence is non-zero only when you have a net source of fluid somewhere within the surface. For incompressible fluids, divergence of u is equal to 0. Okay, the divergence of u is equal to 0 if the fluid is incompressible. If you recall what I said in the last lecture, this means that u can always be written as the curl of some vector. Okay, that means that u can always be written as the curl of some vector. Okay. So, this does not have a simplification in general, because all it means is that you are writing one vector in terms of another. Okay. One vector is being expressed in terms of some other vector. Okay. So, you are not reducing the complexity of the problem. However, it does result in a significant simplification if the flow is two dimensional. Okay. If the flow is two dimensional, so that the velocity is only in one of two directions. Okay. If the velocity is only in one of two directions, okay, we can have a velocity in the x 1 x 2 plane only if I take the curl of a vector that is perpendicular to that, okay, because the curl of a vector is perpendicular to that vector itself. Okay. So, if I have to take the curl of a vector and get a velocity in the x 1 x 2 plane, that means this vector itself has to be perpendicular to that. Okay. So, that means that in the x 1 x 2 plane, this velocity can be written as del cross of a vector that is in the third direction. Okay. So, what this will mean is that u 1 is equal to, or let us expand this out in order to make the point clear. Okay. So, this will be equal to E 1, E 2, E 3, d by dx 1, d by dx 2, d by dx 3, and this vector has a component only in the x 3 direction. Okay, this vector has a component only in the x 3 direction. Okay. So, this gives me E1 partial psi by partial x2 minus E2 partial psi by partial x1. E1 partial psi by partial x2 minus E2 partial psi by partial x1. This is in a Cartesian coordinate system. In other coordinate systems, you just use the equivalent of the curl that I derived for you in the last lecture in terms of the scale factors. Okay. So, this means that the velocity in the one direction is equal to partial psi by partial x2 and u2 is equal to minus partial psi by partial x1. This psi, okay, for these two dimensional flows is what is called the stream function. Okay. This psi for these two dimensional flows is what is called the stream function. You can easily see that with these substitutions, the velocity field identically satisfies partial u1 by partial x1 plus partial u2 by partial x2 is equal to 0. Okay, it identically satisfies that, because when I take partial by partial x1 of partial psi by partial x2 plus partial by partial x2 of minus partial psi by partial x1, it identically satisfies that equal to 0. Good. So, what does the stream function physically mean? Okay. What does the stream function physically mean? Okay. Let us look at okay. If I take the gradient of psi and dot it with the u vector, if I take the gradient of psi and dot it with the u vector, okay, this becomes partial psi by partial x1 u1 plus partial psi by partial x2 u2. u1 is partial psi by partial x2. And u2 is minus partial psi by partial x1. This is equal to 0. So, that means that grad psi dotted with u is equal to 0. Grad psi, note, is the direction of maximum variation of psi. It is perpendicular to surfaces of constant psi. Okay. In this case, since we are dealing with a two dimensional coordinate system, it is perpendicular to lines of constant psi, okay, because a surface in two dimensions is just a line. That if grad psi dot u is equal to 0, grad psi dot a vector is 0 only if that vector is along surface of constant psi. That means that u is a surface of constant psi. Okay, u is parallel to a surface of constant psi. Okay, because I said if you take grad psi dotted with delta x, that will be 0 only if delta x is along the direction in which psi is a constant. Grad psi dot u is equal to 0. That means that u is along the direction where psi is a constant. Okay. That means that the velocity vector is tangent to lines of constant psi. Okay. The velocity vector is tangent to lines of constant psi. Okay. So, these things are called streamlines. Lines of constant stream function are called the streamlines. The velocity vector is tangent to these lines of constant psi, which are the streamlines. Okay. So, if the velocity vector is parallel to these streamlines, that means that there is no flow perpendicular to the streamlines. Okay. So, along the streamlines there is no flow perpendicular to the streamlines. Okay. The stream function also has another important physical implication for two dimensional flows. Okay. If I take a bunch of streamlines, okay, and I take 2 points, okay, and I take some surface, okay, some surface between these two locations, note that the velocity is along these streamlines. Okay. So, what is the integral between a to b? Okay. Integral between a to b of, okay. So, if I want to find out what is the net fluid flow that is coming out of this surface. if I want to find out what is the net fluid flow that is coming out of the surface. Okay. The net fluid flow, we are in 2 dimensions. So, this is per unit length in the perpendicular direction. Okay. So, if I had a 3-dimensional system, this would have been an integral over the surface, but since it is 2-dimensional, it is only over a line. Okay. Q is equal to integral dx, okay, where x is, let me write it as s to avoid confusion, integral ds, okay, that is along the path. Okay. Some differential element along this path is ds. Okay. So, integral ds of u dot n, okay, integral ds of u dot n. Okay. So, this I can write it in the 2 directions as ds u1 n1 plus u2 n2. Okay. Surface of u1 is partial psi by partial x2 n1 plus minus. Okay. Now, if I take a small differential element along this path and I expand it out, okay. So, this is my element ds. Okay. Let me write it a little higher. So, this is my element ds, okay, with unit normal n, with components n1 and n2. Okay. Now, this ds represents an increase or decrease in x1 and an increase in x2. Okay. So, there is a displacement. Okay. There is a displacement along the x1 direction of minus dx1, okay, because it is going in the negative direction. So, dx1 is negative. Okay. So, displacement dx1 which is going in the negative direction, and then there is a displacement in the x2 direction dx2. Okay. So, this, if this is the angle theta, okay, so this is the angle theta between n1 and n. Okay. S is perpendicular to n1, okay, and x2 is perpendicular to n1 and s is perpendicular to n. So, this is also equal to theta. Okay. Okay. So, clearly for this particular configuration, since the angle between n1 and n is the same as the angle between x2 and s, you require that n1 okay, n1 ds is equal to dx2. Okay. That is n1 is equal to cos theta and n2 is sin theta. Okay. Okay. N2 is sin theta and n1 is cos theta. So, n1 ds is equal to dx2, okay, and n2 ds will be minus dx1, because when n2 is positive, the displacement x1 is in the negative direction. Okay. So, n2 ds is equal to minus dx1. Okay. Substituting these into the expression for n1 and n2, you get q is equal to integral, okay, n1 ds is dx2 partial psi by partial x2, and n2 ds is minus dx1. So, you will get dx1 partial psi by partial x1, okay, between these two locations a and b. Okay. This you can easily identify. This is integral between a and b of dx dotted with grad psi. Okay. Dx vector dotted with grad psi in 2 dimensions. So, this is equal to integral between a and b of dx vector dotted with the gradient of the stream function. So, this we know from the integral theorem for gradients is just equal to psi at xb minus psi at xa. So, the difference in stream function between 2 positions tells you how much net fluid flow there is for any surface that connects those 2 positions. From the integral theorem for the gradient, that flow along any surface has to be exactly the same. Okay. You take u dot n across along any surface, okay, which joins these two positions A and B. It could be this surface, it could be that surface, it could be any other surface. I take the net flow across that surface u dot n ds, that will be the same and it will be equal to the difference in the stream functions between the two endpoints. Okay. Of course, along a streamline itself, the stream function is the same. That means that there is no net flow that is going across that streamline, because the difference in stream function on 2 points on the streamline is 0. So, there is no net flow going across a streamline. Okay. So, that is stream function and streamline. Okay. So, those emerged from the definitions of the divergence of the velocity field. Okay. The other thing that emerges is from the curl of the velocity field. Okay. So, when I take del cross u, okay. Once again we will do it in a 2-dimensional coordinate system. Okay. Let us say that along some surface I have a velocity that is now tangential to the surface. So, that u is equal to u phi times E phi. Okay. So, the velocity is in the phi direction, this is r and this is phi. Okay. Now, once again, okay, the integral theorem for this is that integral ds n dot del cross u is equal to integral over surface dx dot u, okay, along the contour that is bounding that surface. So, you can take any surface in the 3-dimensional plane whose contour is a circle along the xy direction. Okay. So, let us do a little calculation once again for this particular value, for this particular velocity field, what will be the curl. Okay. So, we know that in this coordinate system, okay, I have my coordinates I have my coordinates ER, E phi, okay, and I have relations between E1 and E2 and ER and E phi. ER is equal to E1 cos theta plus E2 sin theta. E phi is equal to minus E1 sin theta plus E2 cos theta. Okay. Now, if I take a body that is in solid body rotation, okay, that means that the linear velocity at any distance r, okay, the linear velocity u phi, okay, at any distance r is equal to r times the angular velocity. Okay. The angular velocity omega times r is the linear velocity at any position, okay, distance from the center. So, this is a solid body that is rotating about this central axis. Okay. So, the velocity field is given by u is equal to u phi E phi, okay, which is equal to u phi into minus E r sin theta plus E theta cos theta. Okay. I am sorry, I should write E1 sin theta. And this should be 1 minus E1 sin theta plus E2 cos theta. Okay. Since sin theta is, okay, x2 by r, okay, u phi into minus E1 x2 by r plus E2 x1 by r. Okay. Because x1 is equal to r cos theta and x2 is equal to r sin theta. Okay. Now, I should write these as scalars. Okay. And if I use this form for solid body rotation form, okay, for phi, I will get this is equal to minus omega E1 x2 plus omega E2 x1, okay, because I used u phi is equal to r times omega, okay, which means that the velocity field is u1 is equal to minus omega x2, u2 is equal to plus omega x1. So, that is the velocity field in the Cartesian coordinate system. Okay. One thing you can immediately see, for this velocity field, the divergence of the velocity is equal to 0. Partial u1 by partial x1 plus partial u2 by partial x2 is identically equal to 0. Okay. Now, next if I take the curl of the velocity field, del cross u is equal to okay, if I can expand it out because I do not have a velocity in the x3 direction. So, I just have velocity in the x1 and x2 direction. This will turn out to be partial u2 by partial x1 minus partial u1 by partial x2 in the e3 direction. Okay. I take once again e1, e2, e3, d by dx1, d by dx2, d by dx3 and u1, u2, u3. Okay. u3 is of course equal to 0 and there is no derivative with respect to x3 direction. So, I will get only the partial u1 by partial x2 minus partial u2 by partial x1 times e3. As expected, this curl is perpendicular to the direction of the plane of flow. Okay, it is perpendicular, it is in the x3 direction, perpendicular to the velocity direction, because the curl of a vector is always perpendicular to that vector itself. Okay. And if I substitute these values, okay, you can very easily see that this becomes just equal to u2 is proportional to x1. So, partial u2 by partial x1 will be omega and partial u1 by partial x2 gives you minus omega. So, these will add up to give you 2 omega. Okay. So, the curl of the velocity field at a point for a solid body rotation on any contour, note that this curl that I got for this solid body rotation is independent of r now, it is independent of distance from the origin. It is perpendicular to the direction of the velocity variation and it is equal to 2 times the angular velocity. Okay. This is also called omega, the vorticity, okay, the local vorticity at the flow. Okay. So, the solid body rotation is equal to half the local vorticity. If I take the curl of the velocity locally, calculate that, the angular rotation, the solid body rotation around a point is equal to half the vorticity. Okay. And of course, for this particular case, the Stokes theorem, the theorem for curl should apply, okay, and you can easily show that it does. Okay. Integral of n dot del cross omega will be equal to integral of the surface of n is the unit vector perpendicular to the surface. In this particular case, the unit vector perpendicular to the surface, I should give this a unit vector. Okay, the unit vector perpendicular to the surface is in the E3 direction. Okay, so, I just get 2 omega E3 dotted with E3 itself, this just becomes 2 times omega, okay, integral of the surface. And for this circular surface, this just becomes equal to 2 omega times pi r square, okay, that is this one. Okay. If I calculate the circulation, okay, so this thing is what is called the circulation, okay, integral, okay, of dx dotted with u. Okay. Dx now is along the perimeter of the surface here. Okay. Dx now is along the perimeter of the surface. Okay. The incremental distance along this perimeter is integral r d phi of u phi, okay, which was equal to omega times r. and you can easily see this phi goes from 0 to 2 pi, goes around in a circle. So, phi goes from 0 to 2 pi, and you will get 2 pi r square omega, which is exactly what I had when I did the integral of the curl over the surface. Okay. So, this is basically Stokes' theorem for this particular case. So, there is a net vorticity only if there is circulation around this surface. Okay. Had I taken my previous velocity field, okay, the previous velocity field which had a divergence, okay, if I had this outward velocity field, and if I integrate that over the entire surface, okay, I took the curl of that and integrated it, I would have got identically equal to 0. So, divergence tells you whether there is fluid coming in or out, okay, from the surface. Curl tells you if there is fluid that is circulating around that surface. So, those are the physical interpretations of divergence and curl. Okay. If the curl of the velocity field is equal to 0, okay, I told you in the previous lecture that if the curl of any vector is equal to 0, that vector can always be represented as the gradient of a scalar function. Okay. So, if the flow is irrotational, so that the curl of the velocity field is equal to 0. Okay. If the flow is irrotational, so that the curl of the velocity field is equal to 0, that means that if del cross u is equal to 0, then u can always be written as the gradient of some scalar function. So, for irrotational flows for which the curl of the velocity field is equal to 0, that velocity field can always be written as the gradient of some function. This function is called the velocity potential. It is called the velocity potential. The gradient of this potential gives you the velocity field at any point. For irrotational flows, the velocity potential is well defined in 3 dimensions. Okay. So, in 3 dimensions you get the same result for the velocity potential as in 2 dimensions. Okay. So, this for irrotational flows alone we can write a velocity potential, and you can show that the potential lines, okay, the lines along which the potential varies, and the lines for the stream function are both orthogonal to each other. Okay. So, if I expand out velocity potential, I will get u vector is equal to E 1 partial phi by partial x 1 plus E 2 by partial x 2 plus E 3 partial phi by partial x 3. Okay. Therefore, I have the velocity components u 1 is equal to partial phi by partial x 1, u 2 is equal to partial phi by partial x 2, u 3 is equal to partial phi. Okay. Now, when I had expressed my velocity in terms of stream function, okay, when I had expressed my velocity in terms of stream function, I had said that u 1 is equal to partial psi by partial x 2, u 2 is equal to minus partial psi by partial x 1. Okay. So, if I take the dot product of the velocity gradient and the gradient of the stream function, okay, if I take the dot product of the velocity gradient and the gradient of the stream function, you find that grad phi dotted with grad psi is equal to partial psi partial. Okay. Partial phi by partial x 1 is u 1, partial psi by partial x 1 here is minus u 2, partial psi by partial x 1 is minus u 2, okay, plus partial phi by partial x 2 is u 2, partial psi by partial x 2 is equal to plus u 1. So, this is identically equal to 0. So, therefore, the gradients of the stream function and the gradients of the potential are perpendicular to each other. Okay, or since the lines of constant stream function are perpendicular to the gradients, lines of constant potential are perpendicular to the gradient of the potential, the lines of constant potential and the lines of constant stream function always intersect perpendicular to each other in the fluid flow. Okay. This is not surprising, because I showed you earlier that the velocity was equal to the gradient of the potential, It was equal to the curl of the stream function for two dimensional flows. So, it is no surprise that these two are perpendicular to each other. Okay. So, this gives you some ways of understanding what are the divergence and the curl of the velocity, what they physically represent. Okay. The next step is to look at the gradient of the velocity. As I said, you can always take the gradient, divergence, curl of any vector tensor. Divergence is restricted to vectors and tensors. Gradients you can take of scalars as well, but you can take the gradient of a vector as well. Okay. So, gradient of velocity, okay, grad u. Okay. It has now 9 components. Okay. So, if I write it out in indicial notation, this is equal to partial ui by partial xj. There is no repeated index. That means that this is equal to summation I is equal to 1 to 3, summation j is equal to 1 to 3 of partial ui by partial xj ei ej, the gradient of the velocity field. Okay. We do not usually write these two out in long form, okay, when we just do indicial notation, because there are 2 unrepeated indices. So, it is understood that there are 2 unit vectors and 2 summations. I can write it in matrix form, partial u1 by partial x1 you can write out in matrix form as well. Okay. This is also what is called the rate of deformation tensor. It is called the rate of deformation tensor. What is the physical implication of this tensor? Okay, what is the physical implication of this tensor? Okay. If I have a coordinate system and there is some velocity field with a velocity vector defined at each point within the flow, okay, so there is some fluid flow that is taking place. If I look at one particular location, okay, if I look at one particular location, I have some velocity u. Okay, I have a velocity u. Okay. I go a small distance delta x in some direction. Okay, I go a small distance delta x in some direction. There is a small change in the velocity u. Okay. So, if I take those velocity vectors, okay, there is a velocity u here at x. When I go a small distance away, this velocity has changed a little bit. Okay. So, this has become u at x plus delta x. Okay. And you know from the definition of the gradient that u at x plus delta x minus u at x is equal to delta x dotted with grad u. Okay. The small change in velocity when I travel a small distance, velocity itself is a vector, but still I can define the change in velocity by subtracting out 2 vectors. I have my initial velocity vector, the final velocity vector, I subtract out the 2 and I get the difference. That is equal to delta x dotted with grad u. Have to be careful here, because we are dotting a vector with a tensor. So, I have to write this in indicial notation as delta x j times partial u I by partial x j. That is, the dot product is with the displacement vector and the gradient vector, okay, not the displacement vector and the velocity vector. Okay. So, this gives me the difference in velocity for 2 points that are nearby. What is the implication of this? If this grad u were equal to 0, there is no change in velocity as you move. Okay. So, you have one point which is moving with some velocity. an adjacent point is moving with exactly the same velocity. So, as time progresses, the difference between those 2 points will remain exactly the same. That means that the material line that connects these 2 points does not change, it does not stretch or rotate. Okay. On the other hand, if there is a difference in velocities between those 2 points, that means that the material line element that is joining those 2 points is either expanding, contracting or rotating. Okay. Now, there is a principle of Galilean invariance which states that if you have reference frames that are moving with respect to constant velocities with respect to each other, okay, you cannot generate internal stresses within a system if you just move the whole system at a constant velocity. In other words, if I was having some fluid flow experiment that was going on in some container, if I moved that container with the constant velocity, every point within the fluid moves with that exact same velocity. So, there is no deformation taking place because the fluid moves with a constant velocity, and you require deformation of material elements in order to generate stresses within the fluid. That means that stresses cannot be generated if the entire equipment is moving with a constant velocity. Okay. If I have stresses in a certain fixed reference frame, I take that same experiment and I move the reference frame with a constant velocity, I cannot generate stresses within the system. If the gradient of the velocity is equal to 0, that means that the velocity does not vary as I go from point to point within the system. Velocity is a constant, there cannot be stresses. There can be stresses only if there are gradients. So, when there are gradients, that means that nearby points are not moving with the same velocity. They are moving with different velocities relative to each other. And when nearby points move with different velocities relative to each other, then there are stresses that are generated, okay, due to the stretching of material elements, due to the deformation of material elements. So, this tensor, which basically gives us the rate at which nearby points are moving with respect to each other, gives you the rate at which deformation is taking place, and that is why it is called the rate of deformation tensor. And obviously, any stresses that are generated within the flow cannot be related to the velocity itself, because the velocity, if you move a reference frame with a constant velocity, there should be no internal stresses that are generated within the flow. So, any stresses that are generated within the flow have to be related to the rate of deformation tensor alone. So, I have this rate of deformation tensor and I have expressed it in terms of its components. Okay. I said it will be central in our discussion of fluid mechanics, because all the stresses ultimately will be related to this one. So, if the difference in velocities has a component along the line joining the centers, okay, along the distance between the two elements, okay, if it has a component along that, that means that this material element is being stretched. Okay, if the difference in velocities has a component along that direction, this material element is being stretched. On the other hand, if the difference in velocities has a component that is perpendicular to this direction, okay, perpendicular to the direction, that means that this element is going to get rotated. Okay, it is going to get rotated. So, there are different kinds of deformations. One is stretching, the other is rotation. Now, how do you describe these kinds of deformations without reference to a fundamental underlying coordinate system? So, that will be the next topic of our discussion. Okay. So, this rate of deformation tensor is a second order tensor. It has a total of 9 elements. Okay, it is a second order tensor which has a total of 9 elements. This matrix, okay, any matrix can be written as the sum of a symmetric and an antisymmetric part. Okay. Any matrix can be written as the sum of a symmetric and an antisymmetric part. Okay. So, if I write this in indicial notation, this becomes partial E y by partial x j can always be written as the sum of a symmetric and an antisymmetric part. Okay. Sij plus Aij, okay, where S is the symmetric part and A is the antisymmetric part. Okay. So, you write, for example, if I write this matrix as grad u, this can be written as S, okay, matrix plus A matrix. Okay. How do you get the symmetric matrix? You take the matrix grad u, add the transpose of this matrix and divide by 2. Okay. So, if I want the symmetric matrix, what I do is Sij, I take this matrix, okay, and I add the transpose. What does transpose mean? That means that I change the rows and columns. Okay. The row becomes the column and the column becomes the row. So, what would be the transpose of this matrix? Okay. So, let me write this as the transpose, grad u transpose, okay, is equal to partial u1 by partial x1 that is the transpose. In indicial notation, I am changing the rows and columns. In this particular matrix, the row index was I, because ui by partial xj, and the column index was j. So, I just interchange the two, and so the transpose will simply becomes partial uj by partial xi, okay, and take half of this. Okay. So, this is the symmetric part. Okay. Similarly, you can get the antisymmetric part by just taking the matrix, taking its transpose, subtracting its transpose and dividing by 2. Okay. Aij is equal to half partial ui by partial xj minus partial uj by partial xi. For a symmetric matrix, there are 9 elements of course, but since the off diagonal elements are equal to each other, you get a total of 6 independent elements. Okay. There is the 3 diagonals plus 3 off diagonal elements. The other 3 are equal to the first 3, okay, because the transpose of the matrix is equal to itself. For the antisymmetric matrix, the transpose is equal to negative of itself. Therefore, the diagonal elements are 0 and the 3 off diagonal elements are equal to the negative of the other 3 off diagonal elements. So, that means that there are only 3 independent elements in an antisymmetric matrix, 6 in a symmetric matrix. Sum of these two gives me a total 9 elements in the original matrix. And so, this rate of deformation tensor I have decomposed into symmetric and antisymmetric matrices. Okay. And I can further decompose the symmetric matrix into 2 parts. One is what is called a trace, an isotropic matrix, and the other is what is called a symmetric traceless matrix. Okay. So, Sij, okay, if I write it out in longhand, okay, this is partial u1 by partial x1 half Here is a symmetric matrix, and I can write it as the sum of 2 parts. One is one matrix which is just an identity matrix, which is 1/3, This is what is called an isotropic matrix. It is proportional to the identity matrix. The diagonal terms are all equal, off diagonal terms are all 0, okay, plus a second matrix which I will call Eij. Okay. Note that the sum of the diagonal elements of this matrix, this isotropic matrix, is identical to the sum of the diagonal elements of the symmetric matrix. So, if I subtract out this from this symmetric matrix, the sum of the diagonal elements of that matrix will be identically equal to 0. Okay. So, therefore, if the sum of the diagonal elements of a matrix is called the trace of that matrix. So, therefore, the trace of this matrix, okay, which is basically the symmetric matrix minus this isotropic matrix, is identically equal to 0. So, it is called a symmetric traceless matrix. Okay. So, I have decomposed my rate of deformation tensor into a symmetric traceless, an antisymmetric, and an isotropic matrix. Okay. If you recall, originally I had decomposed it into a symmetric and an antisymmetric. That symmetric further I decomposed it into an isotropic and a symmetric traceless matrix. Why did I do this? Because each of these matrices represents a different type of deformation. Okay. We will discuss it in the next lecture, what types of deformations that these represent. These types of deformations are independent of the underlying coordinate system that you are using to analyze the problem. Okay. So, if I have this rate of deformation tensor, I find out separated into these 3 different matrices. These types of deformation will be independent of the coordinate system used, even though the individual components of this rate of deformation tensor may depend upon the types of components used. So, in the next lecture we will continue this. First, we look at a 2-dimensional system and see what kinds of deformation each of these matrices represent. Okay. And then we will progress to a 3-dimensional system and then look at what are the dimensions in what are the types of deformations in 3 dimensions. This is central because ultimately the stresses will all be related to this rate of deformation tensor later on in the flow. So, kindly go through this and brush up on your knowledge of matrices, so that I can proceed with this, relate this to the rate of deformation tensor in the next lecture. We will see you then.